Hi everyone, my name is Xiaohan. I'm a third-year PhD student at Harvard. Today, I'm really going to keep this talk short because I know you probably don't want to watch it anymore after having so many Zoom calls. And so this is really a very brief story about the UV luminosity function during the epoch of reionization and the physical processes that shape it. So this talk is a compilation of two of my works shown at the right corner here. And if you're interested, please don't hesitate to search for the archive numbers. So let's get started with the luminosity function. So let's focus on the faint end of the luminosity function first. Here is the observed UV luminosity function by Steve Finkelstein at redshift 6. And as we have heard so many times before, the faint end of the luminosity function is shaped by supernova feedback. And then what makes the reionization community especially excited is that the measured faint end slope of the UV luminosity function at these high redshifts is as steep as -2, which basically means there are likely enough ionizing photons from these faint galaxies to make the reionization process possible. However, there is one additional feedback mechanism that possibly complicates the story at the faint end, which is the photoheating feedback during reionization. So what is this photoheating feedback and how does it work? Well, let's take a look at the movie here. So this is a radiation hydrodynamic simulation of reionization that I ran 2 years ago, and here is a visualization of the simulation. On the left, you're seeing the time evolution of the log of the neutral hydrogen fraction. The bluer the color is, the more ionized the gas is. So basically, you're seeing on the left the growth of the ionized bubbles over time. And then on the right, you're seeing the corresponding growth in the IgM temperature. And so as you can see, the reionization process really drives the IgM temperature to over 10 to the 4 Kelvin, which really holds the accretion of gas onto the low mass halos with masses about below 10 to the 9 solar masses. And also because these low mass halos, they have shallow potential wells, their gas reservoir will finally get evaporated. So both these processes contribute to the suppression of the star formation rates in these low mass halos. And so that's the effect of photoheating feedback. And then we do expect that photoheating feedback will suppress the faint end slope of the UV luminosity function. However, is that really the case? Well, we did take a look at this issue in the simulations I just showed here. So here is our simulated luminosity functions at redshifts 7, 6, and 5 from left to right respectively. So these redshifts correspond to half ionized the overlap phase and after reionization in our simulations. And then the black lines are the luminosity functions without radiative transfer, so there is no reionization or no photoheating. The red lines are the luminosity functions with radiative transfer, so there is reionization happening and there is photoheating. However, when you compare the lines of these different colors, you see that the suppression in the faint ends due to photoheating feedback is really hardly detectable, at least for UV magnitudes brighter than -15. So what is this reason for this non-detection of the suppression of the faint end slope due to photoheating feedback? Well, we have to recall that there is not just photoheating feedback that shape the faint ends, there is also the supernova feedback, which actually dominates the star formation process, the regulation of the star formation process. And so what if we run a simulation without supernova feedback? Well, we did that, and the results are shown in the bottom panels here. So again, we run the simulations with and without radiative transfer. But all these simulations are without the effect of supernova feedback. And so this time, as you can see from the bottom panels, the effect of photoheating feedback is really pretty significant. So it suppresses the faint end slope like pretty evidently. And so this really confirms our speculation that the supernova feedback is really the dominant mechanism regulating star formation. And because photoheating feedback is really subdominant, its impact on the faint ends of the luminosity function is really non-detectable compared to the effect of supernova feedback. And so you probably don't really want to use the luminosity function to detect the imprint of the reionization process. And so after talking about this, what else can we learn from observations of the luminosity function? Well, let's take a look at the slightly brighter ends of the luminosity function. So coming back to this plot again, the faint end, as you can see, can be well described by a power law. So the power law fit is shown as the dashed line here. And then when you come to the brighter ends of the luminosity function, it starts to bend over. And that's basically caused by the dust extinction. So what can dust extinction tell us about these early galaxies? Well, it really tells us about the metal enrichment history of these reionization epoch galaxies. And also, it can possibly tell us about the distribution of metals in the ISM. So that means if we have a simulation of galaxy formation and we compare it to observations, we can possibly, this can possibly help constrain the metal enrichment history of the universe, and also let us know whether our galaxy formation model makes sense in the simulations. So that's basically what we did with the SIMBA simulations run by Romeo David. So here's basically what we did. We mocked photometry for the simulated galaxies as shown on the left here. And then we produced the UV luminosity functions for the simulations shown on the right here at redshift 6 and 8 in the top and bottom panels respectively. So this is actually not exactly the way we measured the UV magnitudes for the simulated galaxies, but I just want to show off of the figures here because the images just look amazing. And as you can see, I'm actually producing the mock images at the resolution of the GWST. And so it's pretty interesting to just see how the simulated galaxies look like in the GWST mock GWST observation. And so coming back to the luminosity functions shown on the right here, the dashed lines show the luminosity functions without dust. And then the other line styles show the luminosity functions assuming different dust extinction laws, and also with the assumption that dust traces metals in the simulations. So as you can see, at redshift 6, the SIMBA simulations actually match the observations pretty well. However, at redshift 8, we see that the simulated luminosity function is quite a bit lower than the observations at the brighter end. So that possibly means we have too much metal or too much dust at the brighter end in the simulations. So to look into the reason for that, we looked at the gas phase mass metallicity relation in the simulations. So here on the y-axis, this is the gas phase metallicity, which is also the star formation rate weighted metallicity. The x-axis is the stellar mass. The green line is the mean mass metallicity relation in the simulations at redshift 6. And then the magenta line is the result at redshift 8. The shades here represents 1 sigma spread in metallicity. And the points with arrow bars here are the observations at lower redshifts, redshift 2 and 3 to 4. And so you can see that in the simulations, the simulated galaxies actually have more metals at redshift 8 than at redshift 6. And the simulations actually show more metals at redshift 6 and 8 than the observations at redshift 2. And so this really means that the SIMBA simulations show a very early metal enrichment history of the reionization epoch galaxies, which might seem surprising and maybe a little bit unreasonable because we usually expect that the galaxies at higher redshifts should have lower metallicities. However, we also recall that the simulations actually are in a good match to the observations at redshift 6. So it is possible that the universe really experienced this early metal enrichment. So to answer whether this early metal enrichment history is really possible, we do want to wait for the GWST observations to give us the answers. Well, I finished my talk, really. And here's a brief summary. So I've talked about the luminosity function during the epoch of reionization and the physical processes that possibly shape it. On the faint end, we talked about the photoheating feedback and its interplay with the supernova feedback that actually dominates the regulation of star formation. At the brighter end, we talked about the dust extinction and the hints on the metal enrichment history of the universe. So finally, if you want to create the beautiful mock images for the simulated galaxies using our famous PyLoser code, please don't hesitate to contact me. Well, thanks for listening.